So hyperbolic functions. So what we're going to do in this section is define what hyperbolic functions are, where are they coming from, how are they defined, and well, in this section we will find out how these functions are related and also have differences with the trigonometric functions. And also, of course, we're going to do some calculus of hyperbolic functions. So this is typically a topic that it's covered in a calculus class, even though, I mean, at least the algebraic part could be covered in a pre-calculus course and in an algebra course. We always wait until the calculus so we can cover the whole thing, especially because of the relation with the trigonometry, you know, the trigonometric functions. Well, so hyperbolic functions are combinations of exponential functions, you know, so and they have, again, like I mentioned before, they have some differences and some connections to the trigonometric functions. For example, if we go back to the trigonometric functions, the two main trigonometric functions are sine and cosine. And those two functions are actually what describe the points around the unit circle. Well, of course, it could be a circle of radius other than 1, not just the unit circle, but for the sake of simplicity, we usually talk about the unit circle. And well, these functions happen to be periodic, you know. So if you have some angle theta, whatever that angle is, add 2 pi or 360 degrees, and then you get back to the same point that you were, right? So that's what we got from trigonometry. Now, from hyperbolic functions, yes, it's going to be a very similar relation, but in this case we are not relating points around a unit circle, but rather we are relating points along the unit hyperbola. Well, what do we mean by unit hyperbola anyway? Well, so it's the distance from, you know, when you use the little box to draw the hyperbola, it's 1 unit away from the center of the hyperbola, right? In the same way that it's all the points around the unit circle, well, they are 1 unit away from the origin, right? And well, in this case, these points are not along a circle, and they are along a hyperbola. Well, and of course, there's a notation in this case. So typically, for the trigonometric functions, we use Greek letters like theta, omega, alpha, beta, gamma. Typically we use those letters. However, and that's because those are the letters that we use to denote angles, right? Whether these are in radians or in degrees. But when it comes to hyperbolic functions, because those functions are not related to angles, we still keep the x notation, or the y or the z, depending on the variable that we're using. One of the other differences, as opposed to the trigonometric functions, hyperbolic functions, on the other hand, are not periodic, you know, because these trigonometric functions go around the circle, you get back to the same point, but not the hyperbolic functions. And the notation, notice we have a little h after the name of the trigonometric function, so we call them Sinch, Cos, Tanch, Cos, Sich, and Cosich. These last 3 are a little bit tricky to name, but we actually don't use them very much. And well, one thing, the main point here is the only thing you need to know is these 2 identities right here. From here, we can derive the remaining 4. We can derive all 6 hyperbolic identities. Notice again, there is another relation, another similarity between the hyperbolic functions and the trigonometric functions. So what do we have here? Tanch equals Sinch over cos, in the same way that in the original trigonometry we have tangent equals sine over cosine, cotangent, which is the reciprocal of tangent, which is cosine over sine. And well, secant is the reciprocal of cosine, and last but not least, cosecant is the reciprocal of sine, right? But it's the same in the hyperbolic world, all right? So the first exercise here, the first example is to use the exponential definitions of Cinch and Cos to write down the remaining hyperbolic functions in exponential form. All right, so we already have Cinch and Cos, which I highlighted here at the top. And well, so we can write tanh x, which is, well, first of all, by definition, Cinch over Cos. And then from here we can use the definitions in terms of exponentials. Well, we know Cinch is e to the x minus e to the negative x over 2, the whole thing over e to the x plus e to the negative x over 2. So those are the two definitions of Cinch and Cos respectively. Of course, we can simplify this. We can just cancel the 2's and we will be left with e to the x minus e to the negative x over e to the x plus e to the negative x. Okay? By the way, if you have any questions about what I'm doing here, feel free to stop me at any time. Just raise your hand, right? Let's write the cos function, which by definition, first of all, this is cos over sinh. Well, we are going to use, so rather than actually setting up the whole thing, the whole question, you know, I mean the whole expression like this, we can just use the result from tanh and find the reciprocal, because ultimately cos, oops, I'm missing an H here. All we can do is simply write the reciprocal of this. Okay. And then we have a couple more. Have about sich and cosich. But we know in this case that sich is the reciprocal of cos, and cosich is the reciprocal of sinh, right? And well, if we go back to our original definitions, all we need to write is just the reciprocal of these two expressions respectively. 2 over the difference of exponentials over here. Well, first the sum. And over here, so it's minus. All right. And those are the definitions of the remaining hyperbolic functions in terms of exponentials. Well, so you might wonder, why do we need to know these definitions in terms of exponentials? Well, number one, because when we compute, values or calculations using these hyperbolic functions, if you're using a calculator, for example, not too many calculators have the ability to compute directly hyperbolic functions. So in this case, we need to rewrite them first in terms of exponentials and then do our calculations. And well, the result will depend on what the type of the question that we're working on. If maybe we just want an exact answer, or maybe an approximation to a number of decimals. So that's going to depend. All right. Up to this point, are there any questions about what we have done here? All right, let's move on to the next. Well, so now that we look at the definition of these hyperbolic functions, well, where do they come from? How are they defined? What are their relation? And differences with the trigonometric function. So notice in this case we have, if we have, for example, Sinch, which is e to the x minus e to the negative x over 2, we can split this into the difference of two functions, 1/2 e to the x minus 1/2 e to the negative x. So basically what we're doing is combining two functions together, and in a way of an asymptotic way, that's the end result that we get for the graph of the Sinch function, and the same for the Cos function. So, well, some properties, here to review a little bit of the pre-calculus. One of these functions is odd and one of these functions is even. Can anyone point out which one is the odd one and which one is the even one? Yes.
The odd one is bigger 1 and even 1 is bigger 2.
Well, so this one would be the even one?
Yes.
And this one the odd one? All right, so yes, that is correct. So this one is in the same way. That's another thing in common between the trigonometric functions and the hyperbolic functions. So if we recall from basic trigonometry, the sine function, it's an odd function because number one, f of negative x equals negative f of x. That's the condition for oddness of a function. Or if you observe the graph is symmetric about the origin. That is, if you turn the graph 360 degrees and you end up with the same graph, well, that means the function is indeed, it's odd. All right? And well, the condition for evenness of a function is that f of negative x is, you get back to the original function f of x. Right? And from the graphic point of view, an even function is that is symmetric about the y-axis. Right? So again, a few properties that are inherited from the trigonometric functions to the world of the hyperbolic functions, of course. All right? So let's see. Alright, so how about we compute a few well, now that we look at the definition of these hyperbolic functions, where they come from, what they are, let's go ahead and compute some values. For example, cos of 1. Well, cos of 1, just the way it is, well, we have no idea about what it is. So in this case, what we need to do is convert this cos into its definition in terms of exponential functions. Again, your calculator may not have the ability or a built-in ability to compute hyperbolic functions ultimately. So, well, we know from the definition of cos that, okay, so cos is e to the x plus e to the negative x over 2, right? So let me go back to the definition. So one way to distinguish between the hyperbolic sine or sinh from the hyperbolic cosine or cos is this sign in between the two. It is the sinh, the one that has the minus sign in between, and the cos, which is the one that has the plus in between. Okay, so that's one way to distinguish. Coming back to the exercise, well, so what we do in this case is to replace x in this case with the value that we want to compute. In this case, e to the first plus e to the negative 1 over 2. Well, e to the first is simply e. And recall any number or any symbol raised to the first power is just the number or the symbol. Plus e to the negative 1 over 2. And well, in this case, what you might want to do is to get rid of this negative sign by simplifying a complex fraction. So what do we mean by that? Well, this is the same as saying e plus 1 over e, and then the whole thing divided by 2. And well, there's a couple of ways to simplify complex fractions. So what you might want to think of is having an invisible one here, an invisible one here. And well, in algebra, what you did to simplify these complex fractions, there were two methods actually. One of the methods were to compute the two fractions with the one in the numerator and the one in the denominator, or just find a big least common denominator to kill all the denominators in one shot. I'm going to do that second method instead. And well, what we do to do that is to look at the denominators and find the least common denominator from there. And in this case, we can simplify this when we multiply numerator and denominator by e. So when we distribute, we get e times e, which is e squared, and e times 1 over e, the e's cancel, leaving us with a plus 1. And in the denominator, just multiply e times 2, that's just 2e. All right. And well, that's a nicer final answer. So, and the reason I'm going the extra mile here is because when you're working on exercises like this on the homework, the system may not accept the negative exponent. It might ask you to rewrite this using positive exponents only. So it might tell you that although your answer is correct, it's not written in the form that you are expected to submit it. All right? Questions about this exercise? All right, let's move on to the next one. What do we have? We have a composition of functions, a composition of hyperbolic function and a logarithmic function. And at the beginning, it looks like a little bit complicated, but trust me, it's not as bad as it looks, you know. So, well, first of all, what we need to do is rewrite this Sinch function in terms of its definition in exponential function. So recall that we wrote the Cos function here. Let me write down the Sinch function. Let's recall that Sinch is also the exponentials e to the x, e to the negative x over 2, but in this case with a minus sign in between. All right? Okay, so let's, in this case, we will replace this x, now this x that I'm highlighting, with whatever we have inside of the parentheses of the hyperbolic function. In this case, it's not just going to be x, it's going to be the natural log of 5. So let's go ahead and rewrite this. Plug in that. So that will be e to the ln of 5 minus e to the negative ln of 5 over 2. Right? And yes, it looks a little bit funky. This number looks a little bit funky. However, we can simplify this really, really nicely. Any ideas on what can we do here?
No, you recall correctly, isn't the because e is e and ln cancel each other out, meaning meaning the constant number, in this case being 5.
Yes. So yes, that is correct. The exponential function and the natural log function are inverse functions, are inverse of one another. Well, in particular, let's list those two properties just to recall why are we actually simplifying this. For example, whenever we have e to the ln of x, this cancels to give x. Or when we have ln of e to the x, these two also cancel and lead to x. Well, you learn this in pre-calculus or in intermediate algebra. First, you learn it in the sense of having inverse operators, and then you apply this as a powerful tool to solve exponential and logarithmic equations also. And well, so we're still gonna use these relations for those purposes and a little bit more later, right? Okay, but can I do this also? Yes? Why not?
You have to put it into fraction form, so you have to put 1 over the whole thing.
Put it into fraction. Yes, that's one way. Or the other way, well, number one, the reason why we cannot do that just right away, it's because there is a coefficient in this case. So the property states that we can do only as long as the coefficient of the logarithmic function here is a 1. Well, in this case, we have an invisible 1. So in this case, we're going to take advantage of another property. Okay, whenever we have a ln of x, we can use the property power to product. Oops. Whenever we have a coefficient in front of logarithm, we make it the power of the argument. In this case, well, the variable, which in this case is x. All right, and well, so I call this the basketball smackdown rule. What do I mean by that? Well, when we use it this way, this is like the basketball. You're throwing a basketball, but otherwise the a jumps as a coefficient. It's a smackdown rule. So in this case, what we're going to do is the basketball rule. Make the 5 have the power, the negative power in this case. So well, this we can write this 5 minus e to the ln of 5 to the negative 1 over 2, and only then we will be able to cancel the exponential with the logarithm by the inverse properties of exponential and logarithmic functions. All right, so this will leave us with 5 minus 5 to the negative 1. Yes, I could have written it as a 1/2 in one shot, but I'd rather show all steps, and so I can show you where is this 1/5 that I'm about to write coming from. So 5 minus 1/5 over 2. And of course, we need to simplify this fraction. And okay, we can subtract 1/5 from 5. Well, if we write 5 integer, okay, 5, in this case, the number 5 with denominator 5, this would be 25 over 5 minus 1 over 5 over 2, leading us to 24 over 5, the whole thing over 2. And be careful when reading this kind of fractions. So my advice is to write that fraction that divides the two fractions together a little bit bolder, just so we can make a distinction on how to read this kind of fractions. Because you know what, 24/5 over 2 is not the same as 24 over 5/2, so that's going to be different results. So, or have an invisible one to make it a little bit more clear about how we interpret this. Okay, so when we divide fractions, we keep the fraction in the numerator, and then we multiply by the reciprocal of the fraction in the denominator. And well, 24 goes into 2 12 times, so that's a 12 over 5. All right. Questions about this exercise? Yes. Oh, yes. So do you mean this one? So there is this negative right here. It's exactly. So this negative is the same as saying -1. Okay, let me make it a 1 so it doesn't look like the L from the ln. And ln of 5, and that becomes this -1. If we had like a -2, it would have been to the -2. All right, but yeah, it's typically, I know it's a little bit hard to read because it's only the negative sign without the number. All right. right, so now that we computed a few values using the exponential functions to describe some of the hyperbolic functions, okay, let's move on and now do some algebraic expressions involving hyperbolic functions. Well, so in example number 3, they're asking us to write the expression 7 sinh x plus 4 cos x, but in this case in terms of exponential functions, not in terms of hyperbolic functions. And again, we need to recall what the definitions for sinh and cos are. All right? Recall that the sinh function is, well, they both look the same, except that the sinh function has the minus sign in between, and the cos function has the plus sign in between. So let's go ahead and write this 7 sinh x plus 4 cos x equals to 7 e to the x, e to the negative x. I'm going to write only the exponentials. And you guys will tell me which sign term I'm going to put in between. Okay, the first term, which sign am I going to put in between here? The minus and the plus, right? All right, so let's see. Let's have a look. What are we going to do here? Well, so what we can do here is maybe take out these 2 rather, and make this look like 7 halves e to the x minus e to the negative x plus 4 over 2, which happens to reduce to 2, no? And then from here, how about distribute the fraction and the 2 over each group of parentheses respectively? That's going to be 7 halves e to the x minus 7 halves e to the negative x plus 2 e to the x plus 2 e to the negative x. Well, so from here what we can do is combine like terms. Notice there are 2 different kinds of terms, e to the x's, the positive x, and e to the negative x's. All right, to make this easy to interpret, let's highlight the e to the x's, the e to the x's, to distinguish them from the e to the negative x's. So you can see what am I combining with, all right? So, well, so let's combine the 2 terms that I highlighted in yellow. So 7 halves plus 2. But 2, isn't it the same as saying, okay, 2 and 2, that's going to be 4 halves. So we would be combining 4 halves plus 7 halves. How many halves is that? $11 halves. E to the positive x. Now let's combine. Okay, 2 minus 7 halves. In this case, it's also 4 halves minus 7 halves. Be careful with the signs here. How many halves is that? 4 minus 7. Is that negative 3? And that's our combination of these 2 functions, the sinh function and the cos function, in terms of exponential function. Right? Yes?
What does that cross thing mean every time you put it through the final answer?
Which one? These 2?
The cross thing by final answer, is it?
Oh, it's my way to box the final answer.
Oh.
Yeah. Yeah, that's what it is. Any other questions? All right, let's see what's next. Let's write the following function, sinh of 3 ln of x, as a rational function of x. All right. Yes, we have another very funky looking function expression, but trust me, again, this one is going to simplify really nicely. So it's not always the case that when we combine one type of function with another one, we end up with more complicated function. In this case, well, you'll see what's going to happen here. Well, so number one, sinh of 3 ln x. Let's write down the definition of sinh, which in terms of exponentials is e to the minus e to the over 2, but in this case it's not just going to be e to the x. We have a composition of function, which in this case is 3 ln x negative 3 ln x. The question is, can I cancel e with ln and with ln because they are actually inverse functions of one another? Can I do just right away? Not just yet, because we have coefficients in this case in front of the logarithmic functions. So what we need to do is have those coefficients in front of the logarithmic functions to become powers by the basketball rule of logarithmic functions. So make it a power in this case along with the negative sign. Be careful of that. Alright, so let's see. This will become e to the ln of x cubed minus e to the ln of x to the negative 3. The whole thing over 2. And only then we should be able to cancel out e with ln, and this will be x cubed minus x to the negative 3 over 2. And yes, well, this looks like a function only in terms of x. That is ultimately that's our ultimate goal, to obtain a function of x. Well, but it's not written in the format that we want. So here my advice is to write this denominator as a 1/2 multiplying x cubed, and this second term inside of the parentheses, or rather in the numerator, that contains the negative exponent, rewrite it with positive exponent, 1 over x cubed. Alright, can we make some space here? You'll see why am I making this space here. Well, because we want to combine these two terms together, and well, we need to have a common denominator in order for that to happen. Alright, so you can think of having an invisible 1, and the same way that you would combine fractions together with numbers, we do it with variables as well. We want to make sure that we have the same denominator so we can add up the two fractions together. Alright? So, well, when we multiply these two across, that's a 1/2. X cubed times itself, isn't that x to the 6? Or x to the 9 maybe? What do we do with the exponents when we multiply the two bases? Add them together, right? So that's x to the 6 minus 1 over x cubed. And of course we can bring down this 1/2 as a 2 in the denominator. So x to the 6 minus 1 over 2x cubed. Okay? And that's our final answer. Questions about example number 4? Yes?
Was it really necessary to take 2 out of
This one to turn it into a half? Yes, just so you don't have to deal with to obtain a more complicated least common denominator. For example, if you leave it this way, this way doesn't look like x cubed minus 1 over x cubed, the whole thing over 2. So it's going to look like a funky rational expression, like one of those complex fractions. So having these two in front as a 1/2 makes the expression a little bit more friendly to work with. So, but ultimately, I mean, if you feel comfortable with this and then multiplying numerator and denominator by x cubed in a similar way that we did with other examples, of course we should get the same answer. Multiply x cubed with x cubed, x to the 6, cancel, 2x cubed. Same answer, right? So what I was trying to do here is use different alternatives to simplify complex fraction. In some cases it's fine to do it the global LCD way. In some cases it's convenient to do it by just dealing with one fraction at a time. All right. Okay, so well, again, because hyperbolic functions come from, in a way, they come from trigonometric functions. Well, yes, it's no exception that some of the identities are similar or are related when it comes to hyperbolic identities. So let's see. Well, we already looked at the basic identities, Cinch, Cos, how we call this, the reciprocal identities, the basic definitions. And in this case, well, we have the same idea. Well, this is something we already looked at. So whenever we evaluate the Cinch function at a negative value, the output, it's the same function with opposite sign. This first identity is telling us that Cinch is an odd function, as we already did. We already looked at this, but in this case we did it in the graphic, from the graphic point of view, when we had the symmetry of the graph about the origin. That is, again, if we rotate the graph 360 degrees and you end up with the same graph, or the graph in the same position as originally was, that's an odd function. And the same condition here telling us that the Cos function is an even function. And well, that's when you evaluate a Cos function at a negative value, you get back the original function without the negative. All right. And well, we need to be careful with some of the identities, because well, in this case, what do we have? Cos squared minus Sinch squared equals to 1. Yes, it is similar to another identity from trigonometry. In particular, the one I'm referring to is cosine squared x, or rather theta sine squared. Theta equals to 1, but plus in this case. Or, well, usually we read it the other way, sine squared plus cosine squared. Well, it doesn't matter in this case because it's an addition of two terms and they're both positive. But in the different, order matters. And in this case, well, this cos squared minus Sinch squared, when it's actually going to be our next example, cos squared minus sin squared. So we are going to prove this identity in the same way that you did back in trigonometry. You were given very crazy identities. You used all the basic identities as a toolkit to rewrite the expression, do a series, or rather a sequence of steps, and ultimately, working from the most complicated side of the equation or the identity and getting the right hand side. Typically, that's how we work. All right?